Welcome to this lecture on sampling distributions. Today, we are diving into a fascinating and highly practical topic called extreme order statistics. Imagine you are an engineer tasked with building a suspension bridge over a wide river. You would never design that bridge to withstand just the average daily wind speed. Instead, you must design it to survive the absolute strongest gust of wind that might hit it over the next century. That is exactly what we will learn to model today. Now that we understand why extremes matter, let us define them mathematically. When you collect a random sample of data points and sort them from smallest to largest, these sorted values are called order statistics. We are specifically interested in the two endpoints of this sorted list. The very first value is the sample minimum, representing the smallest observation in your entire dataset. The very last value is the sample maximum, representing the largest observation. Because every new sample yields slightly different extremes, they are random variables with their own unique probability distributions. To predict these worst-case scenarios, we need a mathematical model. This formula gives us the probability density function for the sample maximum. Conceptually, it forces the distribution to shift heavily toward the extreme right tail of the original data. Let us break down the symbols. The lowercase n represents your total sample size. The capital F represents the cumulative probability of your original distribution, while the lowercase f is the original probability curve. As your sample size n increases, the probability concentrates much closer to the absolute upper limits of your data. Before we look at where this formula comes from, let us see it in action with a concrete example. Suppose a factory produces metal rods with completely random lengths that strictly fall between 0 and a maximum value called theta. This means the length follows a uniform distribution. We want to find the probability distribution of the longest rod in a sample of n rods. First, we identify our basic functions. The probability curve is a flat constant, 1 divided by theta. The accumulated probability grows linearly as x divided by theta. Continuing with our calculation, we can now simplify the expression. We substitute our specific uniform distribution functions directly into the general formula for the sample maximum. We replace the cumulative part with x divided by theta and the density part with 1 divided by theta. To clean this up, we combine the theta terms in the denominator. The first part has theta to the power of n minus 1 and multiplying it by 1 more theta gives us theta to the power of n. This final result tells us the longest rod is highly likely to be very close to the upper limit. Now that we have successfully used this formula, let us understand exactly where it comes from. We want to find the cumulative distribution function for the sample maximum. We start with a simple, undeniable logical statement. If the absolute maximum value in a group is less than or equal to a target number x, then by pure logic, every single individual value in that group, from the first to the last, must also independently be less than or equal to x. Because our data points are randomly and independently drawn from the same population, they share the exact same probability. Therefore, we can simply multiply their individual probabilities together. Moving forward from the cumulative distribution, we need to find the probability density function, which gives us the actual shape of the probability curve. To do this, we must take the mathematical derivative of the cumulative function with respect to x. Since we are taking the derivative of a function raised to a power, we use the standard chain rule from calculus. We bring down the exponent n, subtract 1 from the exponent, and then multiply by the derivative of the inside function. The derivative of the cumulative function is simply the original probability density function. This perfectly derives our final formula. Having thoroughly explored the sample maximum, we now turn our attention to the opposite end of the spectrum. The sample minimum is just as important in real-world applications. Think about the weakest link in a chain, or the first component to fail in a complex machine. The logic here is the exact mirror image of what we did for the maximum. Instead of looking at the largest value, we are isolating the very smallest observation in our entire dataset to understand how it behaves as we collect more and more data. Just as we did for the maximum, we have a specific mathematical model for the minimum. Conceptually, this formula ensures that as the sample size grows larger, the probability heavily concentrates around the lowest possible values of the original distribution. Looking at the symbols, n is again our sample size. Capital F is the accumulated probability and lowercase f is the original probability curve. Notice the term 1 minus capital F. This represents the probability of a value being greater than our target, which mathematically forces the distribution toward the extreme left tail. Before we derive this new formula, let us apply it to a real-world scenario. Imagine you buy n identical light bulbs for a chandelier. The lifespan of each light bulb follows an exponential distribution with a constant failure rate called lambda. The chandelier will go dark the moment the very first light bulb burns out, which is exactly the sample minimum. We start by writing down the standard exponential functions. The probability curve describes how likely a bulb is to fail, and the cumulative function tells us the chance it has failed by a certain time. Continuing with our substitution, we can now simplify the algebra. We need the probability that a bulb survives past a certain time, which is 1 minus the cumulative probability. This leaves us with just the exponential term. We plug this survival probability along with the original density function into our general formula for the sample minimum. When we combine the exponents by multiplying and adding, we get a fascinating result. The minimum is itself an exponential variable, but its failure rate is n times lambda. A chandelier with 5 bulbs will have its first failure 5 times faster than a single bulb. Now that we have seen the formula for the minimum in action, let us uncover its origins. We want to find the cumulative distribution for the sample minimum. Instead of asking when the minimum is less than a value, it is mathematically much easier to ask when the minimum is strictly greater than a target value x. If the very smallest number in a group is greater than x, then absolutely every other number in that group must also be greater than x. The probability that a single observation is greater than x is simply 1 minus its cumulative probability. Building on that survival probability, we can now find the final distribution. Since we need all n independent observations to be greater than x, we multiply that survival term by itself n times. To get back to our standard cumulative distribution function, which must measure the probability of being less than or equal to x, we subtract that entire result from the number 1. Finally, to find the shape of the probability curve, we take the derivative with respect to x using the chain rule. The negative signs beautifully cancel out during this step, leaving us with our clean, elegant formula for the minimum. So, we have proven how to find exact distributions for specific sample sizes. This brings us to a broader question. What happens when the sample size becomes incredibly large, approaching infinity? This is answered by extreme value theory. Just as the central limit theorem tells us that averages form a bell curve, extreme value theory tells us that the maximum of a massive sample will always converge to one of 3 specific mathematical shapes. The shape it chooses depends entirely on the tail behavior of the original data, meaning how quickly the probability drops to 0. Depending on that tail behavior we just discussed, the data will settle into one of 3 categories. The first is the Gumbel distribution, which occurs when the original data has a light tail, dropping off exponentially fast, like a normal bell curve. The second is the Freshy distribution, which happens when data has a heavy tail, meaning massive extreme outliers are surprisingly common, like in wealth distribution. The third is the Weibull distribution. This applies when the original data has a strict, hard upper boundary that it can never physically cross, like a test score out of 100. To truly grasp how these 3 distributions differ, let us look at them visually. On this graph, the horizontal axis represents the value of the extreme statistic, and the vertical axis is the probability density. Notice the blue Gumbel curve. It looks somewhat like a skewed bell curve. Now look at the red Freshy curve. Its right side extends much further out, showing that heavy tail where extreme outliers live. Finally, the green Weibel curve drops sharply to 0 on the right, perfectly illustrating a hard upper limit that the data simply cannot pass. As we wrap up our discussion, let us review the most critical points we have covered. Extreme order statistics shift our focus from the average to the absolute limits of a dataset, specifically the sample minimum and maximum. We learned how to derive exact formulas for these extremes using the cumulative probabilities of the original data. Finally, we saw that extreme value theory guarantees that as our sample grows infinitely large, these extremes will predictably settle into a Gumbel, Freshy, or Weibel distribution. You now have the mathematical tools to prepare for worst-case scenarios.